Okay, hello everyone. My name is Anthony and I welcome you to the final presentation of the Cardboard Programming Language Project, CAPL. This is this project where we want to develop a low-cost and accessible tangible programming platform using a tablet-based app. So I will first remind you of what has been done in the previous semesters with this kind of projects. Then I will present you the whole educational robotics system and the app. And after that, in the results section, I will discuss the positive and the negative points about the system, but also, yes, the usability issues that may be fixed in a later iteration of the project. Finally, I will conclude with future work and the new possibilities that this kind of project brings in comparison with what has been done previously. As an introduction, I will briefly present the context of tangible programming platforms. So it has been proven in recent research that the use of tangible platforms for teaching the basics of programming to children can improve their engagement, interest, and collaboration. An important drawback of these robotics educational platforms, however, is that they might be expensive and a lot of schools are not able to afford them. Last year, 2 projects have been conducted at EPFL to develop a low-cost and accessible tangible programming language systems. Andrea Musatti set up the first version of a TPL platform. It was aimed at controlling the tiny educational robot thanks to an external webcam and the tangible tiles. Yes, and I did identifying VPL likes comments. A few months later, Julien Dedley, Noé Duru, and Aditya Mehrotra developed this system. That's a similar tangible programming language for the Timeo as well, but based exclusively on paper and using the built-in camera of a laptop. They called their system paper-based programming language, PAPL. Now, in the same perspective as the 2 previous projects, the cardboard-based programming language project, CAPL, is a tangible platform aiming at setting up a smooth entry to computing education as well. But this time, paper is replaced by cardboard, and even the robot is made of cardboard, and the tablet is used instead of a computer. The tablet can reinforce the tangible aspects and it allows more flexibility in the design of the activities. I will develop the key elements on which the app is based. First of all, I will begin with the cardboard components of the system. The first cardboard-based object I will present is the differential drive robot that we can see here. The number of components needed to build it are very few. As a base for this robot developed by Christian and Aditya, we have a microbit. This is a compact chip made by the BBC that makes coding accessible and that offers plenty of activities that don't require welding. This idea comes from our colleague Amaury Dam, who recently developed another robot based on microbits, actually more than one robot, several robots based on microbits. And the main structure of the robot is made of cardboard, as you can see. And that's the reason why its 2 designers, Christian and Aditya, named it Cardbot. So this simple robot doesn't include any sensor, but a future version of the project could precisely enhance it with the addition of sensors. Now, considering the programming tiles, here are the printed shapes and the support in cardboard. And the programming tiles are obtained by sticking the icons on the support. And then you obtain something like that, as you can see as well on the screen. For simplifying the process of the computer vision, the arranged commands are situated between a start tile and an end tile. And since the current version of the robot has no sensor, we have action tiles only. So it means basically going forward, going backward, turning right, turning left, and turning back. But we have the possibility to integrate even tiles in the case a future version of our robot will embed some sensors. And we also implemented the possibility to integrate for loops with this kind of curved arrows here. So it means that the entire sequence of tiles situated in between these 2 symbols is repeated a certain number of times. For example, here 4 times. So it means that we have here a nested for loop, but this means if we just consider the inner one, that we will go forward 4 times. Now, for coding the computer vision part of this project, I took inspiration of the Python code of the PAPL of last semester, and I used the library OpenCV. This allowed me to develop a working prototype before translating it in Java, because Java is the language used in Android apps. And once everything was working in Java, I slightly adapted the code so that it works within the Android app itself. I will now show you how this computer vision part performs. So this video is not a simulation, but it is a reconstruction of the process that happens in reality in the app. First, the user arranges the sequence of tiles as he wants. Then he takes a picture of his arrangement. We apply some filters to do the rectification step and to spot the 4 corners of the sequence. And after that, we check the correct orientation of the sequence. And finally, we remove the end, the start tile, and we perform the template matching step. So we visit each shape one after the other and compare its contour with each contour of the templates. The template contour, which appears to be the closest one to the contour of the current shape, is considered as being the identified shapes. And this way we can extract the series of commands one after the other. And we get them under the form of strings. Now, the next part is, in order to send this identified commands to the robots, I used the built-in Bluetooth module of the microbit. And this allows the tablet to interact with the microbit as via client-server architecture. The tablet is the client and the microbit the server. And the commands that we got under the form of strings from the computer vision are converted one after the other to simple moves to be executed by the robot, as we can see here. A block-based code is flashed on the microbit, and according to the event the microbit receives, a specific part of the code is triggered, and this makes the robot move as expected. For example, on this side of the slide, we have the block of code making the card move forward when the event D-pad is received with the value button 1 down. Now I will present you the activities I implemented in the app. So the CAPL app is composed of several activities, among which the most interesting are the free game, the geography game, and the Easter egg. That's the dual D-pad controller, which is basically what you just seen in the slide before here. And this allows you to control the cardboard as a remote control toy car, if you want. I will now detail the free game and the geography game. So this free game serves as a base framework for the more elaborated activity, which is the geography game. It provides the features to load the tangible sequence of tiles captured by the camera of the Android device, to interpret these commands, in the case we have some for loop, and to finally send them to the cardboard. This activity allows to freely discover the working of the cardboard-based tangible programming language. And here you see the main panel of this activity. So there is several possibilities to load a picture of a sequence, and then you identify the sequence, send the commands, and I will show you how it works in the next video. I will develop test points while we watch the video. So first here, I just take a picture. You have several possibilities, but I take a picture. You arrange the sequence of tiles, take your picture. Then you send it to the computer vision. It analyzes during a few moments. You got the expected sequence. And then you just have to press the send commands to the robot, and it will be executed by the robot. It's a very simple code, but just for you to see how it works. So the interesting features are that, yes, there is this possibility to integrate virtual tiles as well. And this can allow you to edit actually the sequence that you have taken in picture. And then you can send the code as well a new time. So the interesting features are that you have, yes, nested for loops. Digital tile is to edit the tiles that you have taken in pictures. You have a debug button if you want to debug the code tiles by tiles, comments after comments. A stop button if you have a long command and you want to just set it down. And it allows also to have some feedbacks. So we don't see it very well on the tablet, on the video probably, but if we have an error in the sequence, it will display a message saying that, okay, you have to modify something specifically. The current executed command is highlighted in red, and there is also some information about the for loops, about the iterations in the for loops. Now we'll move to the geography activity. So this is this activity where it is actually a game composed. You have to compose an efficient path for the cardboard, virtual cardboard here, to go from a start point to an end point. And so if you go on water, it costs twice as much as on terrain, and you have to compose this efficient path. So the panel is a little bit more complicated. You have feedbacks as well, and I will just show you on this video how it works. It will be more interesting. You will see that there is also sometimes some questions that might pop up, and test questions might make the robot gain energy or lose energy as well. So this is the real cardboard here. It was on a green screen because I haven't printed it. You compose your sequence. Here I only use digital tiles because it's easier for me. Then the robot moves, and suddenly a question pop-ups. The battery, meanwhile, is decreased. But if you respond correctly, the battery is increased. And then you can send another command to make the robot move again and finally get to the destination. Okay. Now, this geography game also allows you to play, to have several players using this token principle. I will show you how it works. At the beginning of the game, you simply have to specify the number of players you are actually. Here I just set it to 2. And it just behaves the same way. The only difference is that when a question pops up, it is asked then, you will see, to take a picture of your 2 tokens, since you are 2 playing in the game. To prepare your tokens, you take a picture of your 2 tokens. And if the number of tokens corresponds to the number of players in the game, then you will get the points if the question is responded correctly. And then you can simply continue. That's the same principle, but it means that you can play with several players. Actually. Here another questions, and it will be the same process. And once you can see it here, but once you get to the destination, the game is reset. You have a new start point and a new destination point, and you can play endlessly. There is a counter saying you how much time you have reached this destination. And if the battery goes down at 0%, then the whole game is reset and you have to begin again. Okay, now more about the results section of the CAPL project. So since the schools closed in mid-March due to COVID-19, we weren't able to conduct a study about this project in classrooms. But thankfully, we organized the study with 6 primary and lower secondary teachers from Ticino. And we sent them via post some kits with the required equipment and information. And we prepared also manuals, and I made video tutorials to explain them how to build the cardboard and the tiles. And following these instructions, the teachers could hence test the cardboard project and various activities around the microbit. We then scheduled interviews via Zoom that were conducted by Christian in Italian. And they gave us their feedback about the project and if they would consider continuing to use cardboard and microbit in their class. So their feedback is globally positive, but yes, some interviews still need to be done. And to give you a first glimpse of the results from what we see in the interviews so far, the feedback is globally positive. And here are some of their comments about what they liked actually. They think that it would be feasible to do this kind of activity in elementary schools. They like this idea of making with the building of the tiles and the cardboards. They also describe the project as a transversal activity that could be realized as an interdisciplinary project, for example, mixing arts and math. And they seem also to have really liked the idea of having this accessible material that is cardboard, the possibility of customization of the construction of the robots seems to interest them as well, because as they say, it might motivate the children to use what they created. They also told us about what they didn't like. There is a few points, but here only 2 of them. So the technical issues with the app and especially the computer vision. The access to the materials if they plan to use the system at school. For example, not all schools have access to tablets today, so it might be a problem. Now, in addition to the feedback of the Ticino teachers, I made a self-reflecting heuristic of the whole system in order to highlight its weaknesses. And this is based on the list of heuristics elaborated by Christian in his paper of last year, which are the educational relevance, attractiveness, support for collaboration, attractiveness, user interaction, versatility, collaboration and communication, and classrooms compatibility. I went through the whole educational robotics system, so the cardboard-based robot, the interface, so the app and the tiles, and finally the geography activity. And for each of them, so the whole ERS, I just tried to find some technical issues. So in the next slide, I present the results of my heuristic in a chart with following relevance. The usability issues are depicted using shades of red, and the darker a box is, the more a problem it represents. So this chart is here. It represents the importance of the usability issues. On the left, you have the 7 criteria, and here at the top, each of the element of the ERS, and the colors allow us to quickly spot what has to be improved first, what is important to be improved. And I have also related some of the issues to comments from the interviews with the teachers that we have so far. So first, we can see here, the aesthetics of the tiles and the app are cosmetic problems, so it might be improved, but it doesn't prevent the proper use of the system. What is important, however, is that the main concern is the app itself, actually, and especially the computer vision. Because in the version tested by the teachers, the computer vision part was not working correctly, and the app often crashed due to out-of-memory issues while taking the picture. One of the teachers found a temporary solution to this problem. It was, yes, he took a picture with the built-in camera app of the tablet and then loaded it from the gallery. It also works, but that was not the purpose. But in general, the computer vision algorithm also presents more issues. For example, the pictures of the sequence of tiles needs to be taken under certain conditions, no surrounding objects in the field of view, sufficient sharpness, no light reflection in the background, as I have observed. And so all this makes the computer vision not really robust. And in addition, it presents the limitation that the icons on the tiles must have a continuous contour. For example, this kind of contour here wouldn't work because you have two contours. That's the reason why I have modified the start repeat tiles with this kind of contour. And finally, the runtime of this identification algorithm is pretty slow. It runs in 300 milliseconds in Python, but in Java on the app, it runs at least in 3 to 4 seconds sometimes. Then an important point about the app, and hence the geography activity, is that it is currently only available in English, and it could be a good idea to translate the app in different languages, at least French, German, and Italian, to make it accessible to as many schools as possible. An issue about the geography activity is that the questions should be customizable in an easy way so that it can be adapted to specific children regarding age groups, level of study, and so on. On the bottom left corner of this chart, we see issues regarding the classroom compatibility of the cardboard and the tiles. And so yes, of course, it costs a little bit to get the microbit and the electrical components. But what is important is that the cardboard structure should be more robust to be used by children and to have accurate movements of the robots. And it takes too much time also to construct these cardboard elements, especially the tiles that needs to be made accurately to ensure the good working of the recognition algorithm. And it takes at least, yes, 1 hour if you want to produce around 10 tiles. A comment from one of the teachers was, in fact, building the tiles requires a large initial time investment. And in addition, as I presented in the video tutorials, it is easier to cut cardboard with a Stanley knife, but this is, yes, obviously, this is not appropriate for all ages. And as one of the teachers said, since it requires a cutter, it is not recommended to use it in a class. In the end, an important issue is that, as I said before, not all schools have access to tablets and hence have no means to use the system. So this has to be, yes, this has been discussed yesterday in an interview as well. I will now conclude with the novelties of this project and what it brings for future work. So in summary, the work carried out during the semester was to develop an innovative ERS that combined a tangible interface with the do-it-yourself programming tiles, DIY robot, and an Android app to make the communication between the two. And the add-on of the CAPL project in comparison with the time of TAPL and the PAPL is really the framework developed for tablets. The app allows to provide the base for future Android activities around the cardboard, and the Android activities can be easily adapted to various age groups. For instance, by changing the displacement cost of the robot in the geography activity, by including other MCQs, and so on. And in the end, the activities of the CAPL project could foster both teamwork and individual achievements, thanks to the token system and the construction of the cardboard. And now regarding future work, so this project provides a framework for future studies when it will be again possible to physically go to schools to experiment with students. There are, of course, adjustments and bugs to be solved, like the computer vision and the design of the app probably. This is to be done. And the version, it would be interesting as well to have a version for cell phones, so that we can make it accessible to more people. So thank you for your attention, and I know we'd be glad to answer any questions you might have.
Thank you very much. So yes, questions.
Hello, Anthony. My name is Sophia. I have two questions.
Yes.
One question is about the questions that come up on the geographic game.
Yes.
Questions about content, or what kind of questions are there coming? I think it was the slide 15 on the video that you showed to us.
Yeah. Sorry, I didn't heard your question. That was what kind of question it is asked?
Exactly. When they come, what
Okay.
question they have the students when you are on the platform?
Yeah, so it can be easily adapted. I have just to change the code in the app, actually, in the Java file. But the idea would be to make it more accessible. And for this time, I have a question for each box. But to have more time to develop the thing, I have only two questions and replicated them on all the boxes. So the two questions I have, I think it was, what was the name of the country situated at C4? Because you don't see it well, but here you see it well. On C4, you have to go either on the screen of the app or to check on the printed, because there is also this printed map on the ground for the physical robot. You can refer to this map and check at C4 which country it is. And I have also another question, for example, what is the name of the animal that is situated at E7? And these are really simple questions, but it can be easily adapted to various age groups, and depends on the children, actually. But you can customize all the questions based on the location of each box, and each box could have a different question.
And can be the game customize itself? It means that now you have the word.
Yes.
Can we, for example, make a game with a treasure to find a treasure, for example?
Sure. You just have to change a little bit the code and the background, but the basic framework is here. So it means that you can even set a treasure to the goal and change the map. You could, for example, have a Switzerland map or just another kind of map. The principle is that you have a robot that is traveling somewhere, actually, and then you can just customize it as you want. Yeah.
And the price of the robot that you built with the cardboard, do you know?
Yes, I guess we based it on a Bitbuggy car that we bought online. It was 60 Swiss francs, but the thing is that we modified it and we only need 2 servos and 1 microbit. And this could be done, I guess, for around 30 Swiss francs or even less. If you buy several microbits, because a microbit is around 20 Swiss francs, if I remember well, and there is only a few electrical components left. So yes, you can see the robot here. You have the microbit on the top and basically only the 2 wheels. So it's really a cheap robot. I think for 30 Swiss francs, you have easily this robot.
Thank you, Anthony.
You're welcome.
Any other question?
Yes, if I may.
Yep.
I have two questions, sorry. The first one is, you talked at the very end of the presentation about the development for phones, but does it change really something? I mean, when you are
Yes.
building your app, I mean, I know that it changes the layout, so you have to make pretty much everything smaller, but otherwise.
That's exactly it. That's exactly it. For the moment, I just made the app working on TIS tablets, the NVIDIA one. And actually, I haven't tried to make it run on my personal phone. And I have to check how the layout will adapt because I'm not sure about it. But otherwise, it is exactly the same app. So it will work since both devices run Android. There is no problem for the compatibility. The only compatibility that I have to fix is the layout. And I have not tested it yet. But it should be adapted quite easily, I guess, because that's only the disposition of the views and the text views and
The components and stuff like this.
Yeah.
And my other question is, you talked a lot about like the problem with the computer vision. Do you have any suggestions in what direction we should go with this project to improve the computer vision?
So there is two things, I guess. The first one is that it would be important to be able to take a picture of the computer vision of the sequence of tiles. If you want, I have to show you this picture with the possibility to have surrounding objects, because the kind of picture that works is this kind of picture, you see? And there is basically only the sequence of tiles in the field of view. This works, but if, for instance, you have this another tile that is on the top left or top right, it should be, it could make the computer vision crash. So it could be something that can be improved. And the other thing is that we really have to experiment why it is so slow on the app, because I experienced also the thing that when I do the tokens recognition to analyze the number of tokens, it also runs pretty slowly on the app. And there is practically no code, there is no for loop, there is nothing. And in Python, it runs in 100 milliseconds, and on the app again in 2 seconds. So I don't know if it comes from the device or from OpenCV running on the device, in Java on the device. But yes, so there is these two things to investigate, the runtime and the fact that we can take the picture in any conditions. One thing that is important as well is the elimination of the background. If you have some reflection, light reflection on the background, on the table or the ground, it might also not work very well, because it is based on the fact that it recognizes the contour of the sequence. And if you have reflection of the table, the contour won't be like this. It will just be something like this one, you see? And then the computer vision doesn't work, because we have to have the contour of the sequence to spot the 4 corners and then do the rectification and finally go step by step through the sequence. That's some adjustments. Sorry.
One little comment is, so normally I don't think that running Java, OpenCV on Java should be a problem, because I've been using it and I was able to do real-time tracking with many template matching algorithms. So I don't think that the bottleneck is here. And also, you remember I told you about using QR codes. Did you experiment with this?
No, not at all. I didn't change the computer vision since this time, but it would be, as you're right, a possibility. What's the name already of this kind of features that you can track on the
QR codes?
I have it here. I will say it. That's on my other computer. But the thing is, you can of course use a pose estimation trick. Using some marker. That was it, huh?
Yeah, it's marker-based tracking.
Marker-based tracking.
In this case, you have those two.
Aruco markers, yes. You could put them on each corner of the sequence and then try to rectify it more easily. Yeah, could be an idea.
Well, normally the detection and tracking should be very fast.
Yeah.
And you directly have the 3D position.
Yeah, that's it, yes. Yeah.
And I also wondered, well, if there's time for this, what's the
last question
to use for comparing the, for identifying the tile So you say that it's based on comparing contours?
Yeah, yeah. There is a built-in OpenCV function that does it.
Okay.
It's a match shape, I guess. Match contour or match shape. You basically just give as input the template and the picture you have, and then it just match the two contours automatically and give it a distance between the two contours. If the distance is small, it means that the two contours are very similar.
Okay, but this works only with a closed silhouette.
Yes.
Okay.
Yeah.
Maybe you can, well, one possibility could be to use a histogram of gradients in this case.
Yes, probably, yeah. You can, there is probably a few ways to improve this recognition in the runtime, yes.
Mm-hmm.
But that's the main problem, I guess, of this project for now.
Okay. So thank you very much. So we'll stop the question. We will have to move on. So thank you very much.